Hello, class. I'm going to walk you through a couple hundred years of atomic history, and we'll do it in about 10 minutes, maybe. This stuff is not even in your science book. It's just stuff that I think we need to know. If we're going to study the atom, we need to know people who studied it before us and what they did and why it was important. So, you did by now your atomic history note sheet. So these names I'm mentioning, John Dalton, J.J. Thomson, Ernest Rutherford, they should not be foreign to you because you should already have your note sheet done. But this little animation here kind of helps explain it a little more. Since it's not in your textbook, we got a different way to do it. So basically, starting in 1803, a guy named John Dalton, he was curious about matter, and he said, what would happen if we kept cutting matter? If I took an apple and I cut it in half, and I cut it in half, and I cut those halves in halves, and I cut those halves in halves, and down, 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 till we get down to one little bitty thing where I cannot cut it anymore. He was the first person to say that. And he was the first person to say that I'm going to call this matter, this thing that I cannot cut anymore, an atom, because that is what the Greek word atom means, cannot be divided. So he was the first person to come up with this idea, and he was the first person to come up with an actual picture of what an atom was, or matter was, a solid spherical ball. Literally 100 years later, J.J. Thomson came by, and he discovered negatively charged particles that he called electrons. He had this fancy experiment where he shot these, he hooked this, it's called a cathode ray, and these are negatively charged particles coming out of here. He didn't know that they were negatively charged until he put a magnet next to it, and they were repelled from the positive side of the magnet, and they were repelled by the negative side of the magnet and attracted to the positive side of the magnet. So this proved that this coming out of here was not just light. These things were actually negatively charged particles. And he changed Dalton's model to look like a chocolate chip cookie, basically, where we had positive matter and then little negative dots spread evenly throughout. 6 years later, Ernest Rutherford came to test out the model. He did this by shooting tiny alpha particles there, which are very small positively charged particles, through a very thin layer of gold foil, like aluminum foil, but made of gold. How fancy is that? Now, when he did this, he thought the particles would just shoot straight through, like this is showing. But if you see here in the animation, some of them bounce right back. That is not what he expected. So this is the experiment that led him to think what the atom must be. So what we're going to try and do now is recreate this experiment and hopefully try to understand why this is happening. And then we're going to kind of be like Rutherford and draw our own model. Are you ready? So let's see how this works out. So what we have to do is we're going to go to the simulation. Here you have a simulation of the experiment that we're going to try and reproduce. So these are the particles of the gold foil. The red is the positive, and the blue are the negative. So what we have to do is figure out which experiment, how can we manipulate these variables to get the same results that Rutherford did. So do we want to have large particles like this? Do we want them distributed throughout? So the blue particles are negative, and the positive particles are positive. This is kind of what J.J. Thomson thought, that he thought that they look like this, evenly distributed throughout, positive and negatives. So maybe we could start there, because this is kind of what Rutherford thought. What Thomson thought. So the model of the atom has gone from a solid spherical ball to now a two-part model from J.J. Thomson, where the positive and negatives are evenly distributed. So maybe this is a good place to start. And basically what you do here is you change these variables. You change the size and the location of the positive and negatives until you get the same results that Rutherford got in the previous slide that we saw. We were looking for most of those green light things to go through the gold foil, but some of them need to ricochet back at us. So let's start here. Let's see what this one looks like. We got large particles and evenly distributed throughout. Let's see what happens. This is basically showing J.J. Thomson's experiment, if he's correct. Okay. Well, we're getting some ricocheting, but that's way too much. That's not how that worked. So that's not right. Okay, well, maybe let's try small particles. So we're still going to keep them evenly distributed, but we're going to say that they're much smaller. Makes sense because they're atoms, and we know that they're small. Let's see what this one looks like. Okay, most of these alpha particles, which are the green, and you can click right here to see particle traces. I kind of like that, to see where they're going. Most of the atom is empty space, and they're all flying right through. None of them are being ricocheted. Okay, let's maybe keep it small. Let's make the positive. Let's go to clumped core. So now we've changed the model. Now we have the positive protons in a very dense center, all clumped in there together, and the negatives are spread evenly throughout. And again, what we're looking for is most of the particles are going to go through, but some of them are going to bounce back or even ricochet to the side. Let's see what happens. Ooh, that looks good. See how some of them are, anytime one of them hits, so we got a positive coming in at a positive, and they ricochet back just like ping pong, or not ping pong. What am I thinking of? Oh, I can't remember my games. Pinball. Ugh. Yeah, check that out. That looks pretty good. So this is how Rutherford was able to theorize, and he changed the model. He said most of the particles are going straight through, but some of them, whenever they hit a direct hit on this very small positive part of the atom, they ricochet right back. He literally compared it to if you took a shotgun shell from a gun and shot it at a piece of tissue paper, and it came back and smacked you in the face, the bullet. That would be like crazy. Why does this happen? Well, remember your behavior of charges. Opposites attract, similar charges repel. So when we have a positive particle coming in here, most of it is going to get passed right through, but whenever one hits that positive, it's going to get ricocheted or even bounce straight back. This is how Rutherford was able to theorize that the center of the atom has to be a very small, dense, positively charged particle or particles. And so he changed the model. And this is what he thought it looked like. So he went from Rutherford's model, which was like this, evenly distributed, and he changed it to this. Now, he didn't have this fancy animation for him to theorize and do all this stuff with, because remember, we're talking like 1912, I think it was, 1914, something like that. 1908. Got to look at our notes. That's why we take notes. He was literally able to draw and theorize what happened inside here. Why did his experiment happen the way that it happened? It's because of this. And so he changed the model. So you can go to the website that's on the link if you want to and play around with this. Or if you're good and understand what's going on here, answer the question that's on this assignment. It's just one question on the Google Classroom. What is happening here? What did Rutherford discover about the location of the nucleus, the charge of the nucleus, and how did he change Thomson's experiment? Answer that question, and you're good to go.